Hello everyone, myself K. Nitya from the Department of Artificial Intelligence and Machine Learning, St. Joseph College of Engineering, Chennai. In this video, I'm going to explain AVL trees. I'm going to explain the concepts of AVL trees and the rotations involved in AVL trees to make the trees balanced. For this, we need to know the definition for the AVL trees. First, the AVL trees got the name from the three scientists Adelson, Welsky, and Landis. So these three scientists got invented this type of tree, and this tree got this name AVL. Okay. So this AVL tree is one type of a binary search tree because in binary search tree each node contains a value which is lesser than the root node in the left side and greater than the root node in the right side. So here AVL trees also satisfies the same property. That's why we are categorizing this AVL tree in the under the concept of binary search tree. And also AVL tree is also known as self-balanced and self height adjusting binary search trees. So here, apart from the category of a binary search tree, AVL tree is also considered as a self-balanced and self-height balanced and also self-adjusting binary search tree. Why we are calling this AVL tree as the self-adjusting or self-height balanced tree means here in all the nodes a balanced factor is created or calculated for the AVL trees. So here the balance factor means for each node a value is calculated through a formula. So that formula is height of left subtree. LST means left subtree minus height of right subtree. RST means right subtree. That means the balance factor is calculated using the formula height of left subtree minus height of right subtree. That means after calculating this formula, we will get a value called 0, minus 1 or plus 1. So that means the node contains now, the node present in the AVL tree contains either 0, minus 1 or plus 1 only. So, apart from these values, any of the node can get the value other than 0, minus 1 and plus 1 means then that particular tree is considered to be a imbalanced one. So here if a tree contains the nodes with a balance factor of either 0, minus 1 or plus 1 means then that particular tree is considered to be a balanced or height balanced binary subtree. Then that is called AVL trees. But in case while calculating the balancing factor for those nodes in the AVL trees, if any of the node contains the values apart from 0, minus 1 or plus 1 means then that particular binary subtree is considered to be an imbalanced binary subtree. For this only, we are going to perform rotations. So, rotations in the sense we are going to place the particular node which is having the value other than these three values into some other place by rotating the nodes in that particular AVL tree. So, how we are going to perform these rotations? Through two types of rotations. Through two types means the first one is single rotation and the second one is double rotation. So single rotation means we are going to perform only left rotation, and we are going to perform only right rotation. That is called single rotation. And for double rotation, we can perform both left and right rotations or right and left rotations in a single operation in the rotation category. Then that is considered to be the double rotation for the AVL trees. So we are going to find, or we are going to know how these two types of rotations are happening in the AVL trees to make that tree into a balanced binary subtree. So now I'm going to explain about the simple rotations we can perform in AVL trees to make the tree a balanced one. So first rotation type is single rotation. So in this category, we are going to see two types of rotations. One is LL rotation, and the second category is RR rotation. So that means in LL rotation, we are going to perform only left rotation, and in RR rotation, we are going to perform only right rotation in the nodes to make that tree a balanced one. So first, what is mean by rotation? So rotation means we are going to place the node in particular part to another part. That is called rotation. So how we are going to achieve? Let us consider one thread here. So that means if I'm having one thread like this, and here in this thread I am making 3 points here. Okay, in the first point I'm tagging or pasting a paper here, and this paper contains a value 30, 10 and 20. So here the first paper pasted in this thread, consider this line as a thread or a string, and I have pasted three paper pieces with the values carved there as 30, 10 and 20. That means here I am going to perform some rotation in the sense I am keeping this particular point, any of the point I can use that point here in this 30th position, or in this 10, or in this 20 also. If I am going to keep this point as a pivot point, that means if I am placing this particular placing a nail in this particular point, and that means in this point I'm placing a nail and keeping this as a constant position. If and I am pulling the string towards this side, that means I am simply dragging the thread towards the side of the right. Means then what will happen? This 20 will come to this position, this 10 will come to this position, and this 30 will come along this position. Okay, that means I am dragging the whole thread with the papers pasted on this thread. So I will get 30 will come to this point. That means this whole string comes towards this point. That means the 30 will come to this point, and 10 will come to this point, and 20 will follow the 10. So I will get the strings or the thread structure like this. Okay, so that means I'm keeping this point as the pivot point and dragging or pulling the string towards the right hand side, means I am just displacing all these paper pieces along the thread towards the next position. Okay, right, in the right side. So this is called rotation. We are simply displacing the values in the node to other sides. This is called rotation here. So here in this we are going to do only one rotation. That is why we are considering these two types of rotations as single rotation. So now consider this type of rotation, LL rotation. LL rotation means left rotation. Or simply it is left rotation. So left rotation means we are going to perform only the rotation in left side only. So here I am going to explain this type of rotation with one simple example. So consider the values. So consider the values 30, 20 and 10. Here, what type of rotation I am going to perform? It is a single rotation and the category is LL rotation. So in the sense, LL rotation means we are going to perform only left rotation. So left rotation in the sense, I am going to insert a value to the left child of the left subtree. That is why we are calling this rotation as LL rotation. So let's know how it works. Okay. So first I'm taking three values or the three nodes and I'm going to insert these three nodes to construct a AVL tree. So I'm going to explain this step by step. So in the first step I'm going to insert 30 here. So insert the value called 30. So here there is no nodes at all. So if I am inserting 30 into a tree means I am going to create a root node only. So that means if I am inserting a single node or a new node to that particular tree means it is considered to be the root node. So now I am inserting 30. And now for the root node, if there is no children for this, there is no child for this root node means then the balance factor for this root node becomes 0. So here I am mentioning the value of the balance factor at the outside the top of the value 30 here, and this 0 is the balance factor here. And also one more thing, all the leaf nodes of a particular tree will contain the balance factor as 0 only, as there is no left or right child attached to that leaf node. Then that a particular leaf node has the balance factor value as 0 only. And here if one particular AVL tree or a normal tree contains a single node means then this single node can be considered as the root node or as well as a leaf node also. That's why we are making this balance factor for this node as 0. So now I have inserted the value 30 here. That means I have constructed a AVL. I have started constructing an AVL tree by inserting the first node 30 here. So this is the step 1 and I have calculated the balance factor for this node also. And now I'm going to insert the value called 20. So in this AVL tree or in this normal tree, I'm going to insert the value called 20. That means I need to compare this 20 with the value 30 already inserted in this tree. So while comparing 20 with this 30, which one is lower here? The lowest value or the smallest value here is, while comparing 20 and 30 means 20 is the smallest value. That means here the 20 will be placed in the left side of 30. Why? Because AVL trees are following the properties of binary search tree only. So what is the property of the binary search tree? The left node, the value of the left node of a parent node must be smaller than the parent node, and also the value of the right child of the parent node must be greater than the parent node. So that's why we are going to insert 20 towards the right side of 30 here. So now for the first step we have inserted 30, and for the second step insert 20, and also along with inserting the value we need to calculate the balance factor also. So for this, the 30 is the root node here, and while comparing 20 with 30, 20 is lesser than 30, so I am inserting 20 in the left of 30. So now I have inserted 20. Now I'm going to calculate the balance factor. So what is the balance factor for this 20? Consider 20 is the leaf node or root node. So 20 is the leaf node here. So whatever leaf node in the tree we are going to put the value of the balance factor as 0 only. So why? That's why I'm going to put the balance factor as 0, because 20 is the leaf node. And what about this 30? So here the balance factor is calculated with the formula as we have already known. The formula is the height of the left subtree minus height of the right subtree. What is the height of the left subtree here? So 30 is the parent node and the left subtree is having only one level. So the height of the left subtree is 1. And the formula is height of left subtree minus height of right subtree. Is there any node in the right side of this parent? There is no nodes at all. So that means the height of this right subtree is 0. So 1 minus 0, in the sense we are getting the value as 1 here. Okay. So now we have inserted 20 successfully without affecting the balance factor or balance height balance of the binary search tree, because these two nodes contains the balance factors of value 0 and 1 only. So there is no issues at all. Now I'm going to insert the value 10 as the third step. So now if I am inserting the value of 10 in this node, I need to compare this 10 with 30 and 20, as we have already inserted these two nodes in the AVL tree. So now while comparing 10 with this 30, 10 is the left, 10 is the smallest one to the 30. So that means I need to place the 10 in the left side, left subtree of 30. So and again, if now comparing in this node, so 20 is the highest value while comparing to the 10. So 10, in the sense I'm going to insert this 10 towards the left side, left subtree or left child of 20. So that means 30 is the root node and its child, left child is 20, and comparing 10 with 30 and 20, 10 is the smallest, so I am going to insert 10 in this position. Okay. And now 10 means I need to find the balance factor for all these things. So now the 10 is the leaf node. As I have already said, the leaf node contains the value of the balance factor as 0 only. So I am putting this 0 here because there is no left child or right child in this point. And also I am going to find the balance factor for the value 20. So 20 means here for this node, here one left child is there and there is no right child. So for this point only I am calculating the height of the left subtree. So for this there is only one level. So this is 1 minus, as there is no right child, the value of the height of the right subtree is 0. So 1 minus 0, in the sense it is 1. And now I'm going to calculate the balance factor for this node 30. So here the left subtree's height is 2. So I'm going to insert 2 minus, as there is no right child for this node 30. So the height of the right subtree is 0. So 2 minus 0, in the sense we will get only 2. Okay, so now what are all the balance factors values? So the balance factors values will be 0, minus 1 or plus 1 only. So till these two steps, the balance factors of all the nodes are either 0 or 1 only. But here 0, 1 and there is a value of balance factor called 2, which is not one among these three values. So here at this point, in imbalance occurred. So if imbalance occurred means we need to adjust the values of the nodes or adjust the position of the nodes in order to make the tree as a balanced one. So for this, I need to find out which particular imbalance has happened or occurred in this position. So now while inserting 10 only imbalance occurred. So the reason for imbalance at this point is inserting the left child of the left subtree. So that is why we are calling this as LL imbalance. So that is why we are calling this as LL imbalance. So to rectify this imbalance, I am going to perform LL rotation. So LL rotation in the sense the tree is 30, the root value is 30, here 20 and 10. So the balance factor here is 0, this is 1 and this is 2. As the imbalance occurred here, I am going to perform the rotation called LL rotation. That means the imbalance occurred at the left child of the left subtree. That's why we are going to do the LL rotation. Okay. So LL rotation in the sense keeping one particular point as a pivot point and dragging or pulling the string towards the right side from the left. So that's why we are calling this as left rotation. Okay. So left rotation in the sense in which point we got the value of imbalanced factor as 0 or 2 here in this point only. So keeping this point as the pivot point and dragging this whole things towards the right side as the we are drifting. We are just pushing all the left values towards the right side. That is called a left rotation. Towards this means now this 30 will come to this point. This 20 will occupy this 30 along with 10 at this point. So that means while keeping everything towards this point, the 30 will come to this point and 20 will come to the root node and followed by 10 here. So this is the new tree formed after performing LL rotation. For this rotation, we are going to find the balance factor for each and every node. So here 10 and 30 are the leaf nodes. Leaf nodes means then there is no calculation at all because there is no left or right child for all these two nodes. So the balance factor is 0 here and this is also 0. And now for this 20 for this node there is one left child and there is one right child. That means we are having both left and right subtrees. So the height of the left subtree is 1 as there is only one child here. So the height of the left subtree is 1 minus the height of the right subtree is 1, which means 0. Okay, so these all the nodes in this particular tree is having the balance factors value as 0 only. Then that means we have transformed or constructed the AVL tree with the balance factor of 0 by rotating or by performing a left rotation in the imbalanced tree occurred while inserting the value called 10 here. So this is called left rotation and this left rotation is considered as the single rotation only as we have performed only one rotation here. So this is the first type of single rotation. So now I'm going to explain the second type of single rotation called RR rotation. RR rotation means we are going to perform right rotation in the AVL trees to achieve the balanced factor or the balanced height of the tree. So here while inserting the value at the right child of right subtree, then one imbalance may occur. At that point, we are going to perform the right rotation. So for this, I am going to explain this concept using the example value. So I have taken three values as 10, 20 and 30. That means I am going to construct an AVL tree using these values. I'm going to explain this step by step. So for the first step, I'm inserting the value called 10 here. So 10 means I'm simply inserting this. And as this is the leaf node and also the root node for the tree, so consider the balance factor for this node as 0. And I have inserted 10 by constructing the AVL tree. Okay. And now I'm going to insert the next value called 20 in the tree. So insert 20 here. So if I'm going to insert 20 means I need to compare this 20 with the already inserted value 10 here. So that means 20 is greater than 10. So the 20 must come towards the right hand side of the 10. That means the 20 is going to form the right subtree for the root value 10. So I am constructing this 10 and 20 here. So 20 comes to the right hand side and it forms the right subtree to the value 10. So now I'm going to perform the calculation for finding the balance factor. So for balance factor, here 20 is again a leaf node. So the balance factor for this leaf node value is 0. So now if it is 0, then I need to move towards the parent node. So here in this parent node, there is no left tree at all. So if there is no left tree means the height of the left subtree also 0. So 0 minus, that means the formula for finding the balance factor is height of the left subtree minus height of the right subtree. So the height of the left subtree is 0 and the height of the right subtree is 1, as we have only one level in the right hand side. Then the height of the value is 1. So 0 minus 1 is minus 1. So here the balance factor for this node is 0 and the balance factor for this node is also minus 1. So here 0 and minus 1 comes under the values of balance factors. Okay. And then till now, there is no imbalance occurred. Now, I'm moving towards the value called 30 after inserting 20 in the AVL tree. So now, for this third step, I'm going to insert 30. So, for inserting 30, again we need to compare 30 with the previously inserted nodes values. So, now compare 30 with 10. So, 10 means 30 is greater than 10. So, obviously 30 will come towards the right hand side and it will form the right subtree also. So, now for this 10, we are going to insert 30 towards the right hand side of the 10. So in this right hand side, one subtree is there, right subtree, and I'm going to check whether this 20 is less than 30 or not. So now 30 is greater than 20 means I need to insert the value of 30 towards the right hand side of the 20. So the inserted value will be like this. Here 10 and now 20. If I am inserting 30 here, what will be the balance factor for all these nodes? The first 30 node means this is the leaf node. So leaf node, the balance factor for leaf node is 0 and for this node, for this previous node, the parent node 20, there is no left subtree. There is no left subtree means the height of the subtree is 0. So this is 0 minus the height of the right subtree is 1. So 0 minus 1 is minus 1. And now calculate the balance factor for the root node. So as there is no left subtree for this root node, the height of the left subtree is 0 minus the height of the right subtree is 2 here. So that is the two levels are there. So 0 minus 2 is here minus 2 only. Now For this point and for this node, there is no imbalance at all, because all the values of this balance factors comes under the category 0, -1 and +1 only. But for this node, the balance factors value is -2. In the sense, we have encountered an imbalance. So what type of imbalance occurred? We need to find that thing. So what type of imbalance occurred here? We need to find out how that imbalance occurred. Then only what type of rotation we need to perform will be determined. Okay. So now this imbalance occurred only by inserting the 30, the value of the node 30 into this tree. That means this 30 is inserted to the right child of the right subtree. So the imbalance occurred is R imbalance. For this, for remove the imbalance and to make the tree as a balanced one, we need to perform RR rotation. Okay, so for this I am going to perform RR rotation. In the sense, we have 10, 20 and 30 here. This is 0, this is -1 and this is -2. And now at which point we have got the imbalance? At this point 10. So make this point as a pivot value, pivot point, and drag everything towards the left side from this right side. Okay, so that is called our right rotation. We are going to perform the right rotation. So that if I am dragging everything from the right side, means this 10 will come to this point, 20 will come to this position of 10, along with 30 at the position of 20. Then what will happen if I am performing RR rotation? Means what will happen? This 20 will come to this point, means 20 becomes the root node along with the 30 as its right child, and this 10 will come to this point, means we can form this as a left subtree of 20. Now calculate the balance factor for these nodes. So now 10 and 30 are the leaf nodes. So the balance factor for 10 and 30 are 0. The balance factor for both these two nodes are 0, means then what about this 20? Here the left subtree's value height is 1 and the height of the right subtree is also 1, means 1 minus 1 is equal to 0. So here we have encountered the imbalance at this point 10 as -2, but now after performing the right rotation, we have converted this imbalance as to a balanced one using the RR rotation. Okay, so here in this type of rotation, the imbalance occurs only when inserting the value at the right child of the right subtree. That's why we have performed RR rotation, and only one single right rotation have performed. That's why RR rotation comes under the category single rotation. So now we have seen both the two types of rotations, left rotation and right rotation, under the category single rotation. And now I'm going to explain the double rotation concept in detail. Now I'm going to explain the second concept called double rotation. Here also we are going to know or explore about the two categories of rotation, two types of rotations involved in double rotation, as LR rotation and RL rotation. Here we are going to perform both left and right rotations in different manners. in the LR rotation, we are going to perform right rotation at first and left rotation at the second point. Whereas in oral rotation, we are going to perform the left rotation first and then followed by the right rotation in the second thing. So that's why we are going to do two, we are going to perform two rotations in a single time. So we have categorized these two types as under the topic double rotation. Okay, so I'm going to explain this LR rotation with an example as this. So for explaining this LR rotation, I have taken one example value as 30, 10 and 20. Again, I am going to construct one AVL tree using these three values only. Okay, so first I'm going to insert 30. So now there is no nodes in the AVL tree. So I'm going to insert 30 means 30 is the root node as well as the leaf node. So the balance factor for this node is 0 here. Okay, and now we have inserted 30. And what about 10? I'm going to insert 10. So while inserting 10, I need to compare the value of 10 with the already inserted node. So 10, while comparing 10 with 30, 10 is the smallest one. Smallest one in the sense in the binary, according to the rule of binary search tree, the smallest value must come towards the left side of the parent node. So if I am taking this 30 as the parent node, then 10 must come towards the left side of that parent node. Okay, so that means 30 is the parent node here and 10 is less than 30 means I am inserting 10 to the right side, left side of this 30. Okay, so here 30 becomes the parent node and 10 becomes the leaf node. Okay, so now 10 is the leaf node, the balance factor for 10 is 0, and for 30 here there is no right child but there is a left child at all. Okay, so the height of this left child is 1 as there is the only one level there. So this is 1 minus, there is no left right child means 1 minus 0 is equal to 1. So till now there is no imbalance because the balance factors for these two nodes are 0 and 1 only. It is the values of balance factors that is either 0 or minus 1 or plus 1. So there is no imbalance at all. So we have inserted 10 and now I'm going to insert 20 at this point. So while inserting 20, we will see what will happen. So the tree looks like this, 30 and 10. Now compare this 20 with 30 and 10. So 20 is greater than 10 and 20 is less than 30. So less than 30 in the sense, first compare the value with the root node. So 20 is less than 30 means the 20 must come towards the right left side only. So in this left side we are having one more child. So compare the value of 20 with this 10. So now comparing this, 20 is greater than 10. So you need to put this thing towards the right hand side as the binary search tree's rule is placing the biggest value towards the right side of the parent node. So here 10 is the parent node and 20 is the value which is greater than 10. That's why I have inserted 20 in this point. Okay, so 20 is the leaf node also. So I am in the balance factor for the value is 0 and now there is no left child for 10. So the height of the left subtree is 0 and the height of the right subtree is 1 as the level has only one child. So this is 0 minus 1 and this value is minus 1 at all. And now for this there is no right child but in the left side the left subtree's height is 2 as there is two levels. This is level 1 and this is level 2. So the height of the left subtree is 2. So 2 minus there is no right child, so 2 minus 0 is equal to 2. So now comparing these balance factors, 2 means the balance factor, this 2 is apart from the value 0, minus 1 and plus 1. So we have encountered one. What is this? This is the imbalance. Okay, so what type of imbalance we have encountered here? we need to find the imbalance. Then only we can perform the rotation for this imbalance. Okay, so when this imbalance occurred while inserting this 20 node. So I have inserted the node 20 to the right child. That means 20 is the right child's position. Okay, so I have inserted the node to the right child of the left subtree. Okay, so that's why the imbalance occurred is left right imbalance. So we need to perform which type of rotation? LR rotation. That means left right rotation is needed to make this tree as a balanced one. So I'm going to perform these two types of rotations now. So now take this 30, 10 and 20 here. This is 0, this is -1 and this is 2. Okay, so the point at which the imbalance occurred is accountable here. So now keeping these three values, three nodes as the consideration, I am going to perform what are all the rotations? Left and right rotations I am going to perform. So for this I need to perform the right rotation first. The first thing I am going to do is right rotation, then only we can do the left rotation for this balance, for this achieved tree. Okay, so now for this left right rotation I'm going to make this point as the pivot point and dragging every node towards this point. Okay, so that means I'm going to perform the left rotation towards the right side. So while dragging everything towards the left side, in the sense the 10 will come to this point and 20 will come travel towards this point. So the resultant will be like this: 30, 10, sorry, 30, 20 and 10. That means 30 as it is, it remains there itself, and 20 will come to this point followed by 10 in the left side. Okay, so here there is no need to calculate the balance factor because we have performed the only right rotation. So we need to perform also the left rotation. So now I am going to perform the left rotation. We have performed the right rotation. Now I am going to do the right rotation for the second time. Okay, so here the for this thing I have shifted everything 10 and 20 towards the other direction. So now I move towards the point here as the pivot point. Okay, so that means I'm keeping this point as the pivot point or pivot point, and now I'm going to drag everything towards the right side using the left rotation. Okay, so if I am going to do this, means the resultant will be like this: 30 will come to this point, 20 will come to this point, along with 10 to this point. So now the resultant will be 30 will come to the right side and 20 will become the root node and 10 will be the left child of 20. So here one tree has achieved. Okay, so now we have constructed this tree with the help of the rotation. We need to find the balance factor, whether all the nodes got the same balance factor values as 0, -1 or +1, so that we can ensure the height balance of the binary search tree. So now the 10 is the root, 10 is the leaf node and 30 is also the leaf node. So the balance factor is 0, here also 0, and for 20 the left height of the left subtree is 1 minus the height of the right subtree is also 1. So 1 minus 1 is equal to 0. So now all the nodes contains the values of the balance factor 0, which is resultant to the balanced height factor. So we can consider this particular tree as a height balanced AVL tree or height balanced binary search tree. So we have achieved this particular imbalanced concept by performing the left and right rotation. In this, we first I have performed the right rotation, and the second point I have performed the left rotation. So the total rotations we have performed in this method to achieve the height balance for this tree is 2. That means right one and the second one is left. So 2 rotations are needed to make the tree balanced one. That's why we are calling this LR rotation as the double rotation. Okay. So now I'm going to explain the second category of the double rotation called RL rotation. So the second rotation is RL rotation. Here also I am going to perform the two rotations called left rotation in the first step and right rotation in the second step. So we are going to perform double rotations. That's why we are categorized this RL rotation under the double rotation category. Okay. So I'm going to explain this with the same example, but with a different same values in different positions. Okay, so in different orders, 10, 30, and 20. Okay, so here the first thing is I'm going to insert all the values into a tree. Okay, by constructing AVL trees. Okay, so now by inserting 10, what will happen? The first step, we have created one node, and this node is the leaf node as well as the root node. So the balance factor for this node is 0 here, and I have inserted 10, and there is no left child and there is no right child. The balance factor is 0. And now second, I'm going to insert the value called 30. Okay, so now while inserting 30, I need to compare this 30 with the value called 10, which is already inserted in the AVL tree. Okay, so now 30 is compared with 10, and now 30 is greater than 10, which means I'm going to insert this 30 to the right child of 10. Okay, so what will happen? 10 is the parent node and 30 is the right child of the parent node 10. Okay, so now 30 is the left node, leaf node. So the balance factor for this leaf node is 0, and the parent node's value, I need to calculate the balance factor. Here there is no left child, so the height of the left subtree is 0, minus there is one level of right subtree is there, the height will be minus 1, and 0 minus 1 will be minus 1. Okay, so till now the balance factors, there is no imbalance in this balance factors values. Now I'm going to insert the value called 20. I have successfully inserted 30 without any imbalancement, and now I'm going to insert 20. So insert 20 here. What will happen? The tree is 10 and with the value 30 as the right side. Okay, now 20 is compared with the root node. Okay, so 20 is greater than 10, so the 20 must be inserted at the right side of 10. So but there is one right child in this tree, so we need to compare this 20 with this 30. Okay, so now comparing 20 with 30, 20 is the smallest value, so I am going to insert 20 to the left child of this 30 node. Okay, so what is the balance factor? 20 is the leaf node, so the balance factor is 0 here, and for 30 there is no left child at all, so this 0 and that means the height of this left subtree is 1, minus there is no right subtree, so 0, 1 minus 1 is 1 minus 0 is 1 here. Okay, and for this node 10, there is no right subtree, there is no left subtree at all, so the left subtree's value is 0, minus here for this right subtree the levels are 2, so the height is also 2, so 0 minus 2 is minus 2 here. So now comparing all the balance factors of these nodes are here 0, here 1, and here minus 2. So that means one imbalance occurred at this point. So what type of imbalance occurred? We need to find this. Okay, so here this imbalance occurred only when inserting the node 20. So this node 20 is inserted to the left child of right subtree. That's why we are calling this as right left or L imbalance. So for removing the imbalance, we need to perform RL rotation. So I'm taking this same tree, here this is 0, this is 1, and here it is minus 2. Okay, so now I'm going to perform the RL, right left rotation. So if I am performing the RL rotation means I need to do the left rotation first. Left rotation in the sense keeping this point as the pivot point and dragging everything towards the right hand side. So if I am keeping this and pulling the string towards this point without disturbing 10 means what will happen? 20 will come to this point and 30 will come to this point. Then the resultant tree structure will be 10 and this 20 is the left subtree's first value and 30 will follow this. Okay, so now I have completed only left rotation. So there is no necessity to calculate the balance factor at this point. Okay, so now in the second step, I'm going to perform the right rotation. We have completed left rotation. I'm going to perform the right rotation. Now, keep in this point I have kept this 30th node as the pivot point. Now shift this towards this 10 point because here only we got the imbalance factor. Okay, so now keeping this point as the pivot point and dragging everything towards the left side, that means all the right values will come towards the left side. That's why we are going to perform here as the right rotation. Okay, so what will happen? 12 will come to this point, 20 will come to the root point along with the 30 followed by 30 here. Okay, so what will happen? 10 will come to this point and 20 will be the root node and 30 will follow the 20 in the right side. So now we have achieved one tree structure. And what are all the balance factors for these nodes? For 10, it is 0, and for 30, it is also 0 because 10 and 30 are the leaf nodes. That's why the balance factor is 0 here. And for 20, the balance factor is the height of the left subtree is 1 as there is only one level. And for the right subtree's height, it is also only one level. So 1 minus 1 is equal to 0. So all the nodes contains the balance factor as 0. Okay, so that means here the imbalance occurred by inserting the node 20 at this point, and we have performed the left, right and left rotations to make that imbalance as a balanced one. So now this tree looks like a looks as that means this tree is the height balanced binary search tree. Okay, so for this we have performed two types of rotations. The first one is left rotation and the second one is right rotation. So here we have performed double rotation. That's why RL rotation comes under the category double rotation. Thank you all.